Hello and welcome back to Calculus 2. Section 6.10, hyperbolic functions. That's it, chapter 6, last one. And then you can enjoy your exam if you want to. So we're learning brand new functions now. And I have to start with the statement, these have nothing to do with trigonometric functions. They will be called sine hyperbolic, cosine hyperbolic, tangent hyperbolic, cotangent hyperbolic, but they have nothing to do with trig functions. Trig functions will have sets of properties. One of the most important properties of trigonometric functions is that they're periodic. Hyperbolic functions are not periodic. Now, they will share to some extent certain properties. Some identities will be similar, just so enough similar to be confusing. But they are not the same functions. They don't do same things. So you just have to treat them as a completely new bunch. I will start by the definition of hyperbolic functions and where that definition came from. So I will define sine hyperbolic x, and you need to memorize this, as e to the x minus e to the minus x over 2. And I will define cosine hyperbolic x as e to the x plus e to the minus x over 2. So these are the two that you absolutely must know. You know, this is the one of the deal, like if someone shakes you out of bed at 4:30 in the morning and asks you this, you should just recite it. You decide whether you want to punch the person or not, but you got to recite these, all right? And then move on with your life. Now, where do these come from? Well, they come from Euler, the god of mathematics, who realized a relationship between trigonometric functions and exponential functions, and then decided just to check the properties of what's happening with, well, let me just write. So sine x, right, trigonometric function sine x, is equal to e to the ix minus e to the minus ix over 2I, and the cosine x is e to the x plus ix plus e to the minus ix over 2, no I in this case. So Euler figured out that first, the relationship between trigonometric functions and exponential functions. And then he said, if I remove these i's, just remove them, just eraser and erase them, what happens? What happens with mathematics of it, right? So he worked out all of the properties using the e to the x minus e to the minus x, and when he realized what's happening, he decided to name them sine hyperbolic x, because you will see identities. Well, you did the class prep, so you kind of see what's happening there. They resemble trig, but as soon as you look at the graphs of these and basic properties, you see they're not trig, because they're not periodic or anything like that. So that's where the motivation comes from. But then you start going and figuring out all of the applications, and there are many. The most important one, I would say, is, for instance, the cosine hyperbolic x is used for in electrical engineering when you want to compute those cables for power lines, right, between the two towers, or technically any time when you hang a cable between 2 points, the function is not x squared or anything like that. The function for that is cosine hyperbolic x. So there is a lot of other applications out there for many of these functions. But we start from these two definitions, and then we're going to, once we memorize that, we move immediately to tangent hyperbolic x, which is, again, division of sine hyperbolic x by cosine hyperbolic x. So tangent hyperbolic x is going to be sine hyperbolic x over cosine hyperbolic x, which works out, when these 2's are canceled, to be e to the x minus e to the minus x divided by e to the x plus e to the minus x. This cannot be simplified any further, so please don't try to invent more mathematics on top of this. This is it, all right? This is where we stop. because there are plus and minus, right? Addition and subtraction. And because of that, we can't cancel. So now you have your tangent hyperbolic x, and then you will have the other three, which are technically almost never used until we hit the derivatives and integrals, which are the cosecant hyperbolic, secant hyperbolic, and cotangent hyperbolic, because we're going to have the pairing the same way the trig has. So I will write these out, that the cotangent hyperbolic x is 1 over tangent hyperbolic x. Secant hyperbolic x is 1 over cosine hyperbolic x. And the cosecant hyperbolic x is 1 over sine hyperbolic x. So these are the ones that are missing, and I will just, I guess, underline them so you can find them. Now, as it goes with all of the new functions that you learn, you should spend some time staring at the graphs which you can generate using your calculators, because they do have sine and cosine hyperbolic in there, and tangent hyperbolic. I will tell you where they are. Stare at those graphs and learn about the domain and the range and the x-intercept, y-intercept, so all of those properties that you guys know from Precalculus 1, just to get the feel, because these are new functions now, right? And there is no reason not to know as much about these as you know about x squared or e to the x, because these guys are now new functions. Now, when you go into your calculator, TI-8384, which, as we said, we can't use on the test, but you can use them to learn stuff, you will find these in catalog, which is above 0. So you will push second 0, and that will open up the catalog. And then you can scroll down, or you can just use the alpha keyboard. So alpha program will... Hold on. So you go second catalog, and then alpha program to get C, to kind of scroll faster, and just scroll down to C. Eventually you will run into cosine, cosine inverse, cosine hyperbolic, and cosine hyperbolic inverse. So you can type those that way. That's the only way that you can get to them, through catalog button, which is again 0. Second 0 on your calculator, and you can get to these graphs. Now, again, the radians don't play a role, the degrees or anything like that. You don't have to worry about that stuff. So you can find all of these functions. You can draw their graphs. You can explore their properties, and I would strongly recommend you guys do that. You can also see how they look like, so down the line when you're working or engineering stuff, you can see where they fit and use them. Also, another thing that we see from those graphs, they're not periodic, so don't confuse them for your trig functions. Now, why would they have all of these trig names? Why do they borrow so much from trig? Well, some of the properties, identities for these are very similar to your trigonometric functions. And now it depends on how well you know your trig. I'm going to show the formulas now from the textbook on page 493 on the screen. And if you look at these, you will actually be able to find similarities, but they're just so similar that it's annoying, because we know that sine squared plus cosine squared is 1, right? God damn it, right? And you also know, hopefully, that cosine squared minus sine squared is cosine 2x. So those two formulas technically swapped. Look at that. So, yeah, you get the idea how annoying these gets to be now, because the cool thing is that some of the formulas work great. So this one is right on the money, the same as trig, right? Sine 2x and sine hyperbolic 2x. So that's 100% match. Here's your sine is 100% match. But look at the cosine. It doesn't change the sign, right? For the trig part, That was a minus. And now it's plus. It's all courtesy of these i's that are floating around for trig, and they're not floating around for hyperbolics. If you sit down and actually work out e's for these, and you will be, because that's your exam question right there.
I'm sorry, what do you mean by that?
We're going to get into those problems in 35 seconds. So on the exam, you are going to, I'm not doing anything. You're going to have one of these to prove in terms of e's. So technically it's a whole bunch of annoying algebra you do there to show that the left side is equal to the right side. So technically you replace this one by e to the x plus e to the minus x over 2 and then square the whole thing. Minus, replace this with the e equivalent, and then work out that algebra to get 1 on the other end. That's a question. Or maybe this line, or maybe this line. So any one of these, they're all equivalently annoying. It's just basic algebra, but since we are learning this is a new function, you need to know that part as well. Am I going to force you to memorize these formulas, which are hyperbolic identities? I am inclined not to, for one reason, because they get you confused with the trig identities that you actually must know at all times. So if you don't know these identities for the exam, you don't have to worry about it because identity is given and says prove it, right? So what you must learn and must memorize is whatever is sine hyperbolic x and cosine hyperbolic x as definitions, and then you need to be able to grind through the algebra to prove any of these identities. So I will not be asking you to memorize these. Now obviously your coolness factor will grow tenfold if you do. But my primary concern is not to confuse this stuff with trig, because if you do, and then we run into a trigonometric substitution and trigonometric integrals in chapter 7, it's just going to be a bloodbath, all right? So keep focusing on trig identities and no trig identities 100%. If there is extra, hard drive space up there for these kind of things and you can sort them out, go for it. But I will not ask you to state any of these on the test. However, I will pick one of these at random to be proved. So now you let me know which one of these you would like me to do to demonstrate how these things are done. Anyone? I just removed them, I realized. Let me bring them back. So we have, first we go 3 and then 3, so first 6 and then 7, 8, 9, 10, 11, 12, all right? So we have 12. Give me a number. 11 is the cosine hyperbolic squared x reduction formula. Sounds good? All right.
Which one are you doing?
The cosine hyperbolic, the formula 11, second to last.
Oh,
this one.
Good one there. Okay.
Yeah. All right, let's take a look. I will write it now. We have prove cosine hyperbolic squared x is equal to cosine hyperbolic x plus 1 divided by 2.
2x1.
That's what I said, 2x. Please pay attention. All right. So the way we do the proofs is we can either massage one side or the other or both at the same time, hoping to get the same answer. So we can change one side into another, vice versa, or change both of them at the same time and get, I don't know, 1 equal 1 or something else. So I'm going to change both sides here because they're both busy and see what happens. So cosine hyperbolic is given as e to the x plus e to the minus x over 2, everything in parentheses, squared. And I will put the question mark above the equal sign because I'm questioning whether this is the same as what I have to write on the other side. Now, the other side is e to the 2x plus e to the minus 2x over 2, and then plus 1 over 2. Please note the 2's up there because of what? Because the argument of cosine hyperbolic was 2x, right? Fair?
I'm sorry, say that again?
So please, everyone, look at the stream. I'm going to erase this. So look at it now. We all see this one? And now, that's the reason why these two are 2x. Over here, in blue, we had a single x, and then we have the single x's here. Are we all clear on this? So whatever the argument of the hyperbolic function is, that's exactly what you're putting as the argument or the exponent of e. So Control C, Control V. We are going to work out the left-hand side. As I square it, I get e to the 2x plus 2e to the x e to the minus x plus e to the minus 2x divided by 4 should be equal to, and on the left-hand side, the only thing I can do now is to add the 1 as 2 over 2, so e to the 2x plus e to the minus 2x plus 2, everything over 2, everything over 2. So now I'm going just to put over here over 1.
I have a question.
Yes.
How did you get to plus 1 to plus 2?
Common denominator, 1 over 1 times 2 times 2. Adding fractions, right? Awesome. All good. Now, how much is e to the x times e to the minus x? 1. Because x minus x is 0, e to the 0 is 1. So this turns into e to the 2x plus 2 times 1, which is 2, plus e to the minus 2x over 4. And on the other side, multiply 2 that are far apart, which is 1 times the top, e to the 2x plus e to the minus 2x plus 2 divided by 4 on the bottom. Yay, they're the same. Awesome. We're done. So that's the proof. And all of the other ones are done exactly the same way. You write E definitions. You write E definitions for whatever you have, sine hyperbolic or cosine hyperbolic, and then you swap them. How about you do one now because you love algebra so much, right? Let's all together pick something that you really don't like so you can do it now. Pick another one. So 11 is out. This is 11. That's done, right? So that's out. What else? Well, obviously 12 is going to be the same, so you won't do that. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There was this one? Sine hyperbolic x. Okay. Prove sine hyperbolic 2x. No, x plus y is equal to sine hyperbolic x cosine hyperbolic y plus cosine hyperbolic x sine hyperbolic y. Right. Enjoy it. No pressure. You got 18 seconds. If you have a Larson book, this section is in Calc 1 portion of the book, so just find it in the How's the algebra going? Is it annoying enough?
It's annoying.
It's just math. Exactly. Another 10 seconds or so. There's a lot of writing here, so I'm just going to start writing it out. You guys can keep checking. And the key is to FOIL over here. So foiling is e to the x, so e to the 2x. Yes, yes.
That X is all the way across the top. I was going to take a picture. It's a good thing I didn't. I must have been that far right.
In my ad, I'm developing the sign 2x. All right, so FOIL. We have e to the x plus y, and then minus e to the minus x plus y. So that's when we distribute e to the y to both. Now e to the minus y, so that's going to be plus e to the x minus y, and then minus e to the minus x minus y over 4. Plus, and now we distribute the second term, which is e to the x plus y again, and then plus e to the minus x plus y, and now distribute the last one, which is minus e to the x minus y, and then finally minus e minus x minus y again over 4. So looking at these two terms, they have over 4 both, so that's already common denominator. So if I can cancel anything, that would be awesome. Minus e to the minus xy plus 1. So these two terms are the same, and they cancel. And then I have this term and this term cancel. So I cancel them in blue and red. So now when we copy this one more time, e to the x plus y minus e minus x plus y in parentheses like this over 2. On the other side, what do I have? I have this term and this term. They are identical, right? So that's like terms. They add together, so it's 2 of those. So 2e to the x plus y. And then this term and this term are the same, so they add together to 2e minus x minus y divided by 4. And, oh yeah, minus, because of the double negative. And now we get to factor out minus in the exponent, and we also get to cross out this. So we have the left-hand side to be e to the x plus y minus e to the minus x plus y divided by 2 is equal to e to the x plus y minus e, factor out negative, and we get the identical sides. Yay. Thank you for not paying attention. Great. That's that. So a lot of algebra. No one is smiling in the whole classroom. Well, that's okay, because it's a calculus class and we did lots of algebra. Next part is derivatives. See, there you go. Half of the classroom is now happy. Finally, something that we can all understand, right? So, hold on. Can I fit everything? No, that's the best. So, in terms of the calculus portion, we are talking derivatives and integrals. They're going to be, again, right, in opposition to one another. This time, the minus signs are going to go and work differently than trig, so you guys will have to pay attention to that. The rest of the stuff is identical. Another thing is all of the product rules and chain rule and everything else, that still stands there. So we don't get to make this hard, we get to make this annoying, which is the proper definition for what's happening with the next part. So, you know, if you understand that the derivative of sine hyperbolic is cosine hyperbolic, and the derivative of cosine hyperbolic is sine hyperbolic, and then the integrals are going to be the same, just opposite, then it's just a matter of making it annoying with plugging whatever function is in there. So we do have this, and I will write the entire thing because this is something that you all need to know. Luckily, you just need to adjust 2 minus signs. That's all you need to do. The rest of the stuff is identical to the trig portion. So let's see. The derivative of sine hyperbolic x is cosine hyperbolic x, which means that the integral of cosine hyperbolic x dx is sine hyperbolic x plus c. We still have that. The derivative of cosine hyperbolic x is sine hyperbolic x. And I need to warn you that this is where the minus sign is not showing up, right? You know that for the regular trig, you have a minus there. So now the integral of sine hyperbolic x dx is equal to cosine hyperbolic x plus c. So this is the line where there are no minus signs. And you had them in trig. So this is where you have to be careful, this line. Next one. Derivative of tangent hyperbolic x is, guess what? Exactly. Secant hyperbolic squared x, the same as before, which means the integral of secant hyperbolic squared x dx is equal to tangent hyperbolic x plus c. The derivative of cotangent hyperbolic x is going to be cosecant hyperbolic squared x. And this is where the minus signs appear. And I didn't write it. So I'll put it in red. And we have the cosecant hyperbolic squared x dx to be minus, so this is where the minus signs are, cotangent hyperbolic x plus c. The derivative of secant hyperbolic x is negative again, so make sure it's there. Secant hyperbolic tangent hyperbolic. Secant hyperbolic x tangent hyperbolic x, guys, is exactly the same as integrals except no minus sign there. Secant hyperbolic x tangent hyperbolic x dx is negative secant hyperbolic x plus c. And one more. The derivative of cosecant hyperbolic x is negative cosecant cotangent. Cosecant hyperbolic x cotangent hyperbolic x, which gives us the integral of cosecant hyperbolic x cotangent hyperbolic x dx to be negative cosecant hyperbolic x plus c, and we have them all. I'm not going to box all of these, I'm just going to put this. Squiggle here. So we see it, and the interesting part now is that if you are remembering like what the main functions are, sine, cosine, tangent, right, the other ones are negative. Where before it used to be this one was negative, and then that one and that one were negative, this was positive one. So, yeah, if you want to think about being more straightforward, positives and negatives, you can this time around. So guys, you need to know this, but then again, you're supposed to know this, and I warned you about knowing this on the first day for your chapter 7, trigonometric integrals and trigonometric substitution, which is coming up. So now with hyperbolics, we kind of are lucky that all of it works the same except that minus sign, which traveled from the second line into the fifth line. That's it. Using these, we are just going to worry about the chain rule, product rule, quotient rule, use substitution, right? It's just standard stuff. Nothing too crazy. We're going to avoid all of those that actually have to use identities to reduce them so that you can integrate and so on. Because again, it's confusing enough. So, a few examples and we're done. That's the section. Oh yeah, there are inverse as well. Inverse one, if they show up on a test, I will give you those formulas. Again, it's just calculus of those, so integrals. Your textbook has the glossary of about 105 or so integrals. They're part of that as well. We have tools for those today. We don't really have to memorize those formulas. Again, unless you really want to, then go ahead. Right? Some of you always like to undo. Overdo. That's what I mean. So let's first find the derivative of cosine hyperbolic of, I don't know, of something. X cubed plus 4. So what would be the derivative of that? I'm going to actually go into homework and pick up problem from there. So what should I write? Here.
3x squared sine hyperbolic x to plus 1.
Excellent. So I'm just going to underline that this is where you start your derivative. So the derivative of cosine hyperbolic is sine hyperbolic, and it's positive sine hyperbolic. You copy the same argument, and then you take the derivative of it in a chain, which was written in front. So you have the derivative of the inside, which is a chain rule, written in front. That's awesome. So that's correct answer. That's all. Perfect. I'm going to hit few of these from the textbook. Here's the great one. Find the derivative of the square root of cotangent hyperbolic 3x.
What problem was that?
This would be 26. The one above is I made up the first one. The first one is similar to 22.
I think that's it.
Did you put your money on? That's what I was about to ask. I'm not sure if I did it right. You did, I think you did. Me? Yeah. I did it right? Yeah. Yeah, you put that in square because of the difference.
I hope you guys are seeing that this is a double chain rule, right?
Yeah.
Double chain over here.
Uh,
So there should be a cosecant square floating around. Hyperbolic. what we call an evil problem for no reason. No reason to do this. Like in any application.
What are hyperbolic functions used for? Like,
you probably missed the first part when I talked about you zoned out. You can watch the stream back, we'll say.
It's for the wire, like the wire cables, they're using for that,
To model.
to model.
Yes. All right, so we are going to start by 1/2 and then cotangent hyperbolic 3x to the negative 1/2. So that's the derivative of the outside times the chain, which is the derivative of the inside. Derivative of cotangent is negative cosecant hyperbolic 3x, and then we have one more chain, which is a 3.
you missed the square.
No, it's right there. Please look. See? Squared. That's definitely squared. It was maybe just too small from where you... Ooh, I have even the better one. Or maybe on Apple is differently written.
Go back.
Go back.
This one, I haven't finished.
Go back. I'm not done yet.
Oh, okay.
I still have ways to go. It's going to be a division line because of the negative 1/2. 1/2 is a square root. Negative pushes it downstairs. So we have 2 square roots of cotangent hyperbolic of 3x. And on top we have a negative 3 cosecant hyperbolic squared 3x. I'm just going to make sure that the squared is visible right there. There we go. So that would be the derivative. You will expect pretty much the same thing from trig. It's about, in terms of calculus of these, it's the same amount of annoyance, except you just have one extra letter to write, the age. Have to be careful with the minus sign, right? Where's the minus sign? One more? Because you love it so much. Let's see. Ooh. This next problem is problem 27. And we're going to take the derivative of ln, whose argument is secant hyperbolic 2x. Right? I will go around. It's a double chain. Double chain. And then you put everything on one, right? The tables.
1 over on top of G. 1 over, yeah.
Oh, and simplify.
Yeah, but what's the okay.
I can send some disturbance in the force, so I'm just going to work out the ln x of f of x, whatever that f of x is f of x, f prime of x, right? All right, try again. What's f of x in this case?
2x.
Nope.
No.
Secant
Oh,
2x.
secant x.
So that's where the double chain is coming out. The 2 will come out eventually as well. So try it again. That would make it worse. You got me over there.
Oh, yeah.
Did you cross out the correct one? And wrote something before the You got it?
I think so.
Nice.
It will just become negative 2. Negative 2. Cool. I survived from the initial. Just probably how quickly it is. I'm not, is that the one where there's like a demo on the PlayStation where like they discontinued it because it scared people too much? I think that was one game. It was like around the corner. Jump scare game. Yeah. No, one actually gave me the heart attack. So they discontinued the game because his family sued me. Like a man actually died playing the game.
We're good? Okay. I learned that from a dog. It's on. All right, let's take a look at the problem. So with logarithmic function, we will take the derivative of logarithmic function. We'll take the argument, write it as is in denominator, and take its derivative in the numerator. Derivative of the secant is negative secant tangent. So negative secant hyperbolic 2x tangent hyperbolic 2x, and then we still have times 2 in the chain rule because of 2x. These two cancel because they are the same, and we end up with negative 2 tangent hyperbolic 2x as the answer, and we're done.
What about the LM?
Oh, I forgot.
I'm sorry, yeah. Oh, sorry.
Okay. So for integrals, we have to watch for u sub, I would say about 98% of the time, and then those 2% would be if it's a basic integral. Because you really don't have any other integration techniques. And I told you that I won't bother you with the identities, the problems that have to use identities first, because the identities, I don't want you confusing that stuff with the standard trig formulas that you must know to survive chapter 7. So for integrals, we have some basic stuff like, let's say, what is the integral of cosine hyperbolic of 5x dx, right? We start with the most basic of all. And that would be what?
Sine
5x over 5. Ah, I see how it is.
I said that you just want to listen.
Oh. It's amazing how much you're going to pick up on everything else that I say. All right, great. What's the next problem we're going to talk about? Let's see if we can figure out, how about cosine hyperbolic x divided by 10 plus sine hyperbolic x, because you're so good at it. How about that one?
Is failure an option?
Yes. Yes. Failure is always an option, as well as quitting, as well as, yeah. And some of you disagree, just by looking at the facial expressions. So is this a basic integral? So it's a u sub, right? That's how difficult the first exam actually is. Like, oh, it's not a basic integral, then it's a u sub. Like, you have no options there. The second test gets to be very interesting. It's like, which one of these 300,000 different options do I get to use? Like now, if it's not basic, it's u sub, you're done. So what's u? 10 plus, okay, good. Keep going. So if it's not basic, it's u sub. Great. Well, then there's du. Then you're gonna present. Did you forget plus c? Awesome.
Professor, will we actually get points off if we forget the plus C?
It's just -1. Don't worry about it.
Whenever you don't forget the DDX.
Yeah, ddx is -5 per time. Yeah. You have to worry about dx. That's the one. Like plus c is just -1. Forget dx on any of the lines. That's the one that hurts.
Is that cosine?
It's coming up.
Like x dx?
Yes. Yeah, so this is like -5 right there. On a question that is worth 8 points, you get like -17 off. So that's bad. Yeah.
Correct me. So it becomes 1 over u because the du, since it's cosine hyperbolic x, it turns that upper
Yeah.
1 into a 1.
Can you write the full thing out?
So here it is. This is in a peanut over here. You have this one over here. Fair?
Yeah.
So that's going to be your du.
Yeah.
So now if I write it, it's du divided by, and let's go with, purple is red. That was red, but that's fine. So that's u,
Gotcha.
which we can write as 1 over u du because we know that the fractional multiplication, right, if you write it on the side, multiplies only the top. So ln absolute u plus c, that was great with the absolute values. They're not there for decoration. We talked about the issues with the domain and why we must have them. 10 plus sine hyperbolic x, and then plus c for that final point that we all want on the test. Awesome. What happened?
Even if you get
Like 3 of you talking at the same time. If you have the problem wrong and you have plus c, then the problem is just wrong.
So you still don't get the +1 even if it's wrong?
No, you will definitely get +1. You will lose other 9 points on it. Yes.
I can deal with that. That's a big compromise.
Yeah, and then you have 7 on quizzes. I mean, that's 8 points. Like you are allowed to completely obliterate one. I have no clue how to do this integral. Plus c, that's it. Blank plus c, and then you have +7 coming in from the quizzes. So one problem you covered, right?
You get 600 points for signing your name, so that's good.
Yeah, I should actually do that. 600 on the first test. 600 points for writing your name. That sounds good. I'll make a test out of 1,000,000 points. So.
And if you get a 0, then that's like awful. Like your name.
Oh, the SAT? Yeah.
There's a guy that got 0 on the SAT.
How about like 300? That means every other letter of the name is wrong. Wasn't sure how to write them R's, T's, and G's, right? The rest of the letters he was sure about. And the name was George. Wow. Can't write G, right? And R. Bad. All right. Ooh. Here's one you're gonna. In my eyes, right? People watching this or listening to the stream, I was like, what the hell is going on in the class? My eyes just lit up. I saw this problem. It's better to ask it here than on exam.
Yeah, please don't, if it's that bad, don't put it on the exam.
No, this one is
I swear to
this one
God.
is a peach.
I swear to God, you just wasted once on the test.
Now, how about we do this one in groups? All right. Talk to people that are sitting next to you or around you. Migrate if you have to. Try to figure out. This is how chapter 7 trig is going to look like at minus 80.
I'm just gonna go out on a limb here and say, is it cosecant hyperbolic squared, which is negative cosecant hyperbolic?
Are you doing this in your head?
Yeah. No, bro, look. I'm just saying, it's a theory. It's because if you know the what's that? If you know the
You already have the memory? You don't have the
I
memory.
have a screen right here that helps out.
My wife has.
That's awesome.
You
Well, the
don't do
graphic,
that, of course you have.
I'm a programmer, but it just a lot of times most programmers you gotta recognize patterns. So if you recognize patterns, that's what I'm saying. If this is the same thing as this, right? It's just reversed. Could, yeah, so the antiderivative of this is negative cosecant hyperbolic. So since these are
Plus C.
yeah, plus C. But since it's squared, does that account for something? Does it make it 2? Yeah. It's a theory. Yeah, so because it's squared, you can write 2, negative 2, like negative 2 cosecant hyperbolic x squared plus 6 from the square. I think that's right. It's a theory. Because I know what you, like if you was to find, like for example, if you know like sine squared x, I'm using a different example, the integral for that is 5 cosine squared to negative 2 cosine. Oh wait, then that would be right?
What's originally
Not the negative two.
That's just, isn't that
I'm not arguing the negative. I'm like, two.
well, just because it's squared.
yeah, yeah, because of change. So, like the way I remember the chain rule, so if you have like it's just the outer part, you do the derivative of the outer part times the derivative of the inner part. And if it's double, you just keep working your way inside. So like when we were doing so you do the outer part times the derivative of the inner part. So, like, for example, when you have the doubles, it'll be like, okay, so the outer part, like, for example, when we were going with the double derivative, so I just rewrote it as this, and then the derivative of the outer part is here, times the derivative of the inner part here, times the derivative of this inner part. So, you just multiply those three. Then here, because this is a negative cosecant.
So that makes it negative 3 and 3x.
Or you yeah. So the 3 comes from 3x. The negative, alright.
This negative 3 comes from negative 3.
Yeah. Yeah, so it's just keep finding it. So it's you work your way from the outer part in. That's how I remember it. So that's like my theory of how this one goes, but I'm not sure. So because of the chain rule, it will be negative 2 cosecant hyperbolic x. Yeah. Plus c. Just the theory. I absolutely have no idea. If I get this wrong, I'm sorry. That's what I'm saying. Because if you did this, because pretty much if you square each thing, that's the same thing. Oh my god. How did you come? Because this you can rewrite. There we go. We can this whole thing is squared, right? It's the same thing as if it was to square each piece, right? Like if I rewrote this, is this.
You only need to do is to take the derivative to get that thing. You do it. You don't take. You can take the derivative.
There we go.
I never learned that.
Because
You never learn why.
like he's saying, so I wrote it. Just saying, I wrote it.
Your career goodbye. Right now.
Be squared, right? So if
Or
you
you
do
can
this,
get home.
Is that like Precalculus?
that would be.
So your way actually
Yeah. No, but it's not quite right because you have to find the answer of the square here. So
that's what we're talking about.
this now, but this becomes 3 over 3, and then you multiply that times.
Here we're not taking.
Yeah, this is like my case. Then from there, we'll find the antiderivative. So if you make this a u, like u sub, and go from there. So u is equal to.
Yeah. It's right.
Yeah, add to be u.
And then to make, and then you have to, you need to
U would be.
Is it?
There's nothing to cancel.
You just integrated it like.
do I write it down? And it doesn't want to be
So that way you can do the
This is your time to shine.
in life.
Actually,
because no, we can't use that. The theory was somewhat
She's going to just go outside, just go there.
square goes up in age.
If you get the derivative of
Awesome.
yeah.
You gotta love the way things pair up.
Yeah.
The singing of the pattern.
You can also just guess the first and then get lucky. Because there's only 2 options.
Go get my master.
What are you trying to get your master's
But it's in science, business, makes a master's in data.
So you do data.
I'm a data analyst. I'm not a programmer, I can do a little programming, I'm teaching myself Python, but it's kind of hard to describe what it is.
No, I get because data analysis. So pretty much you study like data patterns,
Data
like
patterns,
predicting the
yeah.
future.
Yeah, exactly.
Actually-
And finding the pattern. I work in healthcare market research. So it's about, finding the patterns of where the market is moving, what drugs are being approved on what formulas.
That's really interesting.
And considering how old I am, I don't keep moving forward. Really improving the job. So, yeah.
I can't do that.
Is that-
Just do my own laws.
I'm 56. So I'm really unique to people. They pay me. Oh my God.
I was close. I was somewhat close.
So we can't use the U substitution.
In the ballpark, let's just.
In the ballpark, but that was third and I thought that was first. It was around. It was a theory.
Well, maybe.
Yeah, do 10 problems. Look at that.
Is that correct?
Yeah, why not? It's good.
Well, back to those things.
Awesome. Oh, I just spotted -5. There you go. And another -5. That's -10. It's just like you haven't even done this. And then another -1 over here. So that's the entire problem for -11.
Don't do anything with that yet. I do that. Please. Now be boss out.
All right, let's talk about this. This is awesome. Great job. For our comrades from NJIT with it. So we know that we can take the derivative, sorry, the integral. Oh, sorry, the derivative. We are looking for function derivative pair. We know that the derivative of cotangent is cosecant squared, and we have the cosecant squared. So we are going to save that piece for du, which means that this has to be u, and it's going to be u squared. So that's how you figure out what's what. And you will be sick of this in chapter 7 when we do 7.3, 7.4. 2 sections of just this. Figuring out which is the function derivative pair, which one is, but it will be done with a trig, but it's identical.
I have a question.
Sure.
This is a handwriting issue. This is -1/3.
U is upstairs because the integral of, right, integral of
U cubed.
U cubed
plus
over
C.
3.
Okay. Thank you.
It's u. So this is perfect solution. We have the cotangent hyperbolic x to be u, and then we'll have to square it because it was squared. And then when you do the du part, solve for dx. This is one of the ways to do it. It's fine. Dx, replace dx with what dx is, and then these cancel. Or you can just say, well, I have cosine squared, right, which is this underlined. You just put the -1 instead of it. Whatever way you want to do it, it's fine.
For the answer, is that cotangent hyperbolic cubed x?
Yes.
Okay.
And then you have the answer to be u cubed over 3 plus c, and then u cubed is cotangent hyperbolic cube x. And that's it. That's perfect. All right. The class ends in 10 minutes, right? Which is, yeah, I'm going to just write this solution out on the stream over here, so it's part of the lecture. And then we're going to talk about the exam, because we are done with section 6, chapter 6, sorry. We're done with the chapter, and we need to talk about the exam. So let me just write this in 1 minute. So u is equal to cotangent hyperbolic x, du is equal to negative cosecant hyperbolic squared x dx. I'm going to underline this, and notice that it's a negative du that goes instead of that. So I have negative integral u squared du, which is negative u cubed over 3 plus c, which works out to be negative 1/3 cotangent hyperbolic cubed x plus c, and the problem is done. So that ends, as I said, for inverses, inverse functions, inverse hyperbolic functions will be, formulas will be provided. So you will have to just plug in and so on if anything shows. So just try a few of those plug and pray kind of thing, and it should be fine. All right, so that's it. Let's talk about the